Our project concerned lithium-air batteries, which is an emerging new technology that could potentially replace gasoline. Lithium-air batteries have a potential energy density to be 5 to 10 times what lithium-ion batteries produce today. So the energy density is comparable to gasoline and potentially could replace all gasoline engines in automobiles. This would be greatly reduce fuel emissions as a result of automobiles and could be a very good thing for the world. However, there are a lot of concerns and challenges facing the lithium-air battery, least of all that lithium reacts with water very violently. And we decided to focus on the challenges related to the cathode. The cathode in a lithium-air battery is oxygen. Oxygen is what gets reduced and is supported by a carbon structure. So we decided to study the way lithium peroxide deposits on this carbon structure. The lithium oxidizes at the anode, moves across the electrolyte, and then reduces the oxygen at the cathode. This creates a deposit of lithium peroxide. There's a problem with the way it deposits, and currently if it deposits too thickly, it will cause the battery to stop working because the electrons won't be able to reach the reaction site. So a big problem with studying these electrodes is that when you move them from the argon-filled glove box, where you disassemble the battery, to the SEM machine for imaging, there's an exposure of air that necessarily happens. So our solution was to make these aluminum cups, which we then put in the glove box, took the cathode samples out, placed them in the cup, affixing them with carbon paper, and then we sealed it with copper tape, as you can see here. This whole unit was then put into a foil bag that was thermally sealed and brought to the SEM machine. At the SEM machine, we removed it from the foil bag, and this is the key part. We put it in the SEM machine, and inside the vacuum of the machine, we were able to remove the copper tape without disturbing the sample. This was able to ensure that our lithium peroxide was not oxidized by atmospheric exposure, and our carbon cathode sample was preserved just as it came out of the battery. This is important because this is a hot area of research, and a lot of research is being done to overcome these challenges in order to produce this battery. And in order to produce this battery and overcome these challenges, you need a reliable mechanism to analyze the results. This allows a reliable transportation mechanism, so that way all SEM and TEM results can then be analyzed properly, conclusions can be drawn, and the battery can be produced commercially, hopefully in 5 to 10 years. Thank you very much.